Very warm welcome to everyone to our Support Vectors weekly paper reading. Today, we are going to read an interesting paper, Reinforcement Pre-Training. This paper is about a little more than a month old, and it has some surprising results. Uh, it also raises some quite interesting questions about um, the broad applicability of reinforcement learning in the full training of an LLM. So I'll give a brief sketch of what we are going to do. We are going to cover uh, this paper carefully, then we'll take questions. Please keep the session interactive along the way. If you have thoughts, comments, please do jump in with those comments. Remember that this session is recorded, so do not mention anything that may be your company confidential or in any way violate your privacy. So if such a thing happens, let us know and we'll align that section from the video. All right. So this paper is from Microsoft and Tsinghua and Peking University. Obviously, these are significant research powerhouses. What this paper does is it revisits the pre-training of large language models. So to set the context, I will mention the traditional model training pipeline, LLM training pipeline. Traditionally, what we do is we have a pre-training step, and in the pre-training step, what we do is you take a large corpus, ginormous corpus, typically 2 to 10 trillion these days, tokens, or 1 to 10 trillion tokens, let me just put it this way, tokens. And then you play this game on an LLM in which you apply, you take a sentence from this or a text from this, and then you ask it to, you say, the happy cow jumped over the, and now you have to figure out what it is. Very roughly, in a very simplified form, you play this game with this LLM, and the only way this LLM can answer that question is if it has a pretty good understanding of human language along the way. And so if it can say, jumped over the moon, for example, it's doing pretty well. This is your what people call the pre-training of the model using next token prediction task, next token prediction task. And when you do that, you apply your classic negative log likelihood function, log likelihood, log, or the basic loss function that you would typically apply to such a task. At the end of this pre-training, what comes out is what people consider a model that has learned to understand. It has an understanding of the human language, or NLU, natural language understanding. However, it is not aligned to human expectations and human values. So then we go through two further stages. Paradoxically, or somewhat of an oxymoron is used for this. It is called post-training. So-called post-training. So there is further training that is often called the post-training stage, and it usually involves a supervised fine-tuning. So you have some input and then you say, this should be your answer. And after that, the second thing you do is RLHF, reinforcement learning with human people. In other words, the humans ascribe a certain amount of reward, goodness to the answers. And from that, first reward model is trained, and that reward model then helps the reinforcement learning process, and the policy optimization takes place. So this is a typical three-stage, the so-called three-stage training of a large language model as started by the Instruct GPT paper, for example, amongst other things. People often call it instruction training of the GPT. And there are many, many words that people have used. Obviously, to call further fine-tuning and RLHF training of a model as post-training is a bit of an oxymoron, but the vocabulary, for some reason, has stuck in our industry. So this is the typical thing. With this as a backdrop, there has been a further development. As we know, around February 2025, a landmark paper came out, which was the DeepSeek R1. And what the DeepSeek R1 is observed, or the remarkable insight it came to, is that you can actually greatly improve the reasoning capacity or the induce reasoning in a large language model through pure reinforcement learning with verifiable rewards. Like give them math problems, give an LLM math problems, give an LLM programming problems, which you can verify using parser, etc., a compiler, or unit test, whether it's correct or not. Things like that. You have verifiable rewards. And if you train that, so amongst the many things that DeepSeek R1 discovered, perhaps the most landmark thing that it discovered was that you don't have to do chain of thought training of our LLM by giving a lot of chain of thought examples and in trying to induce reasoning in the model by supervised fine-tuning with COT examples. That doesn't quite work, which is the approach people had been taking. And what DeepSeek showed is that you just have to step back, do just RL, reinforcement learning with verifiable rewards, and wait. And as you continue training, successive steps of training gradually leads to the emergence, most remarkable thing, the emergence of reasoning spontaneously on its own. Right? So this spontaneous emergence of reasoning capability in the machine was, I think, the landmark contribution that the DeepSeek R1 paper made to this. So after that, there has been a lot of activity using DeepSeek's R1 paper. And the DeepSeek R1, just to remind you, use group relative policy optimization. So the RL optimization method that it used was GRPO, group relative policy optimization. So we will see that in this paper too. Now, while many of us have been busy applying GRPO, and then there have been subsequent sort of evolution of GRPO into other policy optimization methods downstream. We have been trying those. There has also been another sort of a startling set of results coming from research labs like Anthropic and DeepMind and so forth. A whole body of work seems to claim that reinforcement learning does not teach a model anything new. It only sharpens or accentuates prior learning, which the model has through supervised fine-tuning. Right? So what, and that's a statement that is too early to tell how it will work out, but there seems to be some corroborating evidence towards a hypothesis like that. I must say outright that I'm a bit skeptical of a strong statement in that direction. I'm much more inclined, and this is my position on that, to a weaker position, which is to say that if you apply reinforcement learning to a model that has gone through supervised fine-tuning, it will predominantly sharpen or accentuate prior learning. But there is also scope for new learning. For example, otherwise it would be hard to explain how DeepSeek R1 could spontaneously develop reasoning abilities. So that is my perspective. So now, with all of this, a flurry of activity in the industry happening in the last few months, in which people are very excited about GRPO, excited about pure RL, and at the same time, there's another body of evidence of wondering um, how much how much of this is real, or whether they should be a bit skeptical of this. But this paper is sort of lands in the middle of all of that. So I thought I'll contextualize where this paper lands. And what this paper argues and shows convincingly is something quite clever. It says, why limit RL or reinforcement learning only to the so-called post-training phase? Why not the first part of the first pre-training part that happened, next token prediction task, why not apply RL to that also? And that's exactly what they do, and hence the title of this paper, which is reinforcement learning, uh, reinforcement pre-training. In other words, we're applying reinforcement learning to the pre-training stage itself. But actually, the way they do it is a little bit odd. They don't start with a blank model with uninitialized weights. They start with Quen, a 14 billion parameter model, into which DeepSeek R1 has been distilled. So this is something actually, as we read through this paper, I thought I'll mention it because it might create confusion along it. So they have somewhat redefined the notion of what is pre-training, and it departs significantly from the classic notion that Instruct GPT paper put forward. What this paper does is it says, okay, let's start with it says that let's start with Quen 14b R1 distill, and I might get the order of the wordings wrong, but basically what you do is you take a Quen a 14 billion parameter model, and into that, um, so let's start with this. Yeah. So I will call it the base in this discussion. Today, I will call it the base model. So let's ponder a little bit about the base model. If you look at Quen 14b, Quen 14b has gone through pre-training with just next token prediction over a ginormous corpus, let's say a web corpus. I'll use the word web, but it includes social media and all of that. Whatever data that you can gather, it has been. And you just play the next token prediction game, and you use the loss function associated with this. So this is the first thing it has been through. It has also, as a base model, I suppose if it was released, it must have gone through some further internal alignments. But then DeepSeek R1 is distilled into the model model using, I mean, it's basically a direct into the above model, right? Inducing some reasoning capabilities, some reasoning. Because if you remember, R1 was all about a reasoning, it is a reasoning model. So now, as we remember, the DeepSeek R1, it was distilled, and the authors of DeepSeek R1, the original paper itself, went about distilling R1's reasoning capability into a host of other open source models, right? Llama and Quen and this and that. So you do that. So this, you would imagine that at this stage, it has already through fine tuning, supervised fine tuning, so it has been done that through a distillation process. Now they are saying this is the base. What ends up here is the base. And instead of saying that we enter the post-training stage, they're saying, let's go back and redo the pre-training, but this time change the loss function. Instead, do reinforcement learning. So you say revisit, let's say step 1. So or maybe let me write it down clearly. Step 2, step 3, revisit next token prediction, like in step 1, but as a reinforcement learning task. What is that and how do they do it is actually pretty interesting. Uh, what they are saying is, typically an LLM, you give it a fill in the blank, it produces a probability of probability over the vocabulary. Suppose you have a vocabulary, and I'll just oversimplify by saying, let's say that the first word in the vocabulary is aardvark, all the way to last word is, let's say, zephyr. Then it will create a probability distribution over the vocabulary. Right? And from that, by sampling off, using some sampling method, you would pick the next token. And then if the next token isn't what you expect, obviously you will have a negative log likelihood. That is how step 1 was done above. But instead, what you do is you say there is a reward, verifiable reward, which is very simple. You know the ground truth. So suppose you gave the sentence, the happy cow jumped over the, this is the token. What you could do is you could ask this machine, this LLM, right, to produce, let's say, G predictions. Right? It can produce, you keep iterating. This is the standard GRPO process. GRPO process. You make it produce this. Now, anytime it predicts an answer that is not the word moon, moon happens to be the ground truth. If it doesn't predict the word the moon, you give it a reward. Model will say, if for next token, reward for the next token, moon, 1, all else, 0. Right? So you have a very clear rewarding policy, very explicit rewarding policy that intuitively emerges from the ground truth itself. You say, if you predict the right word, you get 1, and that is what this statement is. They take a slightly different statement than the one that I took. And so I'll go through this paper sort of back and forth, but I would actually start with this particular example. There's this electric forces grow with charge. Electric force grows with charge, right? Now, just a background knowledge that electric forces grow with charge size, right? That is the Coulomb's law. So now this machine is asked to predict all sorts of things. Now GRPO says that you have to think of G, different repetitions of the prediction. You keep feeding in the same input G times. Each time you see what is it that the model predicted. The first time the model predicted polarity, the second time model predicted size, and the third time model predicted and. And so because size is the right answer, you give a reward of 1 then, and for all other cases, you give a reward of 0. Right? Classic reinforcement learning, and especially the GRPO approach to it. And therefore, you can now convert the next token prediction into a RL exercise in which you insist that the model must produce a thing, just like the DeepSeek, and thing, and then the answer. the actual answer, where it could be, let's say, size, right? I think in their case, the answer is boxed into, let's say that the answer is written as boxed size. But basically, this is your standard DeepSeek terminology, urban terminology. So what happens is you're saying, don't just predict an answer, give a reasoning, give a reasoning trace of why you pick the answer, pick the token. Okay. What is the question being asked? Is your microphone on? Yeah.
Yes. So Bobby has a question. They say, how does the reward get determined? Is it a manual process?
Oh, no. The reward is determined quite literally from that. See, you know the ground truth. You know that the ground truth. You picked up a sentence from the web corpus, the happy cow jumped over the moon. Right? So if I give only this as the input, then I know that I'll give a positive reward, a reward of 1 only if the machine produces moon as the answer. Moon is the next token. For all other predictions, it has to give 0 as the answer. So what you do is, and this is the point I was going over, namely that you take the LLM and you feed in this, the happy cow jumped over that's your statement. You do it, it will produce prediction P1 or the token T1. Then you go repeat the process. You feed it in again, it will produce T2, feed it in again, it will produce T3, G times TG. Now, of all of those times, if it ever produces the right word, namely moon, right? Let's say that T3 was the moon. So the reward R3 will be 1 and all other rewards will be 0. That is what this picture is trying to say. And I'll repeat this. An illustration of reinforcement pre-training. Given a context with a missing continuation in the next token, the LLM performs on policy rollout to generate G different thinking trajectories. This is typical RL speak. You basically say that you have to give a reasoning why you're going to pick a next token, and then you have to produce the next token. And you have to repeat it G times. That is a GRPO. Each includes an intermediate reasoning step and a final prediction of the next token. A positive reward is assigned if the prediction matches the ground truth token. Otherwise, the reward is 0. So, Bobby, I hope this clarifies it. The corpus, the web scrape data itself gives you the ground truth. It gives you the reward model because you know that the ground truth word is moon. Therefore, the very easy reward model is if the machine says moon, give it a reward of 1. In all other cases, give it a reward of 0. And this is it. And then from this it learns. This is your standard RL. Does that? Yeah. Go ahead, please.
Yes. So I'm just kind of from looking at this at first glance. I'm trying to really understand the difference between this and GRPO, because is this method like where they're keeping yeah, I guess that's probably where I'm confused. So any way to clarify that would be much appreciated.
Now, Elsa, they use GRPO. It is no different from GRPO. The only difference is they are applying the GRPO directly to the pre-training, the next token prediction task itself. That's all. That is the key insight of this paper. Apply GRPO, go back and apply, and this is the point I'm trying to make. You go back and revisit the next token prediction task on which the model was pre-trained, revisit it, but this time apply GRPO to it. Right? So if you look at it, the signature of figure 3 is classic GRPO, right? You produce G results, and then you give rewards. And here the ground truth is known because you know which word to predict. Go ahead, somebody is asking a question.
Yeah. So I had like a different question. So in this context, like giving a zero reward for the non-exact match. So we have like a similar word for size, like maybe different word. And won't be this problematic because with a different word having the same meaning as a size, and in maybe another context it makes sense there.
Saurabh, that's a pretty astute observation because language comes with synonyms, right?
Yeah.
Or it could have just said something that would have finally brought in the word size. And in the approach that they have taken, the preliminary approach that this paper refers to, see, it is breaking new ground. It's saying we did this and it worked, right? So they took a very simplistic approach. Unless you get an exact match, your reward is zero. Even if you come up with a synonym that happens to be correct, your reward is still zero.
Okay.
So this opens the door to further refinement in subsequent research or subsequent effort, where they will probably accommodate for synonyms. But in this first effort, they have not done that.
Oh, by the way, like if they mention, are they mentioning this kind of thing in a limitation or like scope of a paper?
I don't remember seeing that
Okay.
actually. Right? See, look at the thrust of these researchers. What they asked is a pretty good question. Why can't we apply RL to the next token prediction task with which we pre-train models? And what they found, and see, this is often, these sort of papers are often proof of feasibility, right? A proof of possibility, the fact that you can do that. And when you do that, look, it leads to remarkable results, as we'll see in this paper. Even doing something as simplistic as this, like as you pointed out, they took a very simple approach. If you don't get it exactly right, you get a zero reward. You get a remarkable lift, quite a remarkable lift in model performance. And so this entire paper's, the core idea is that we need to bring in RL even to the next token prediction task. Nevertheless, when they use the word pre-training, it is a bit unorthodox use of the word, because everything that people do after next token prediction, the web corpus, we usually ascribe it to post-training. Like you do supervised like distillation using supervised fine-tuning, you do any kind of supervised fine-tuning or RLHF, etc. Most people would have bracketed it as a post-training or subsequent. People use all sorts of words, but that they would have put it in that category. In an unorthodox use of words, they say that actually this is still pre-training, and I believe they're right. But the way to interpret this stage is the step 3 calling it still pre-training is because pre-training is an unsupervised task. You do it on a vast amount of web scrape data, right? Or this in which you use that when you do a next token prediction, you already know, you just randomly pick a sentence from the web scraping and then hide a word and you say, what word is that, right? Next token prediction. That's why it was so feasible to train or pre-train models with trillions of tokens. And what this paper is saying, and let's come to the core of it. It's saying that, see guys, when you do RL in post-training, let's say you do supervised fine-tuning after the pre-training, you do it with hand-created data. Right? Supervised fine-tuning data is limited data. It is not in the scale of trillions of tokens. It's very, I don't know, 1 million rows or something like that. It depends upon what you take for supervised fine-tuning. Or if you do reinforcement learning after that, RLHF or just RL, whatever it is that you do it again with limited data. You don't do it with unlimited data, right? But think about this. We are going back and revisiting next token prediction itself as a RL task. So the scale of RL now suddenly opens up. I don't think explicitly did it in this paper because they actually did it on a limited data set, the OmniMat data set, but it opens up the possibility now that you could force it to, or you could apply this method to the vast corpus that you have scraped from the web. And because you can theoretically do it there, they still use the word pre-training to step 3. They say step 3. So it's peculiar. Pre-training, then some supervised fine-tuning for distillation, DeepSeek distillation, followed by again pre-training. And they're saying we are taking the Qwen 14B with R1 distillation as our base. And then we are restarting the pre-training process all over again, but this time as a reinforcement learning task. Does that answer your question?
Yeah.
And
So,
that
but
is a-
I'll say that, yeah. Sorry, go ahead.
No, finish your thought.
Yeah, like I didn't get like an exact answer, but though whatever you discuss about makes sense, right? Yeah, it's just a continuation of this brilliant idea. We might see more about that thing later on.
That is true. And this sort of research always leads to a whole flurry of subsequent research that will come after that. So anyway, I suppose the main idea, and I'll just revisit the paper in detail, but the results just speak for themselves. For example, a Qwen R1, even with R1 distillation into the Qwen 14B, the model prediction accuracy was approximately, let's say, 30%. But the same model, absolutely the same model, you take it through a reinforced RL process for next token prediction task itself. And all of a sudden, you notice a substantive jump to close to 34% accuracy, which is comparable to a much bigger model. If you notice, R1 Qwen 32 billion parameter model, which is more than double the size, you begin to achieve accuracies comparable to a much bigger model. Right? And that is the main point they're making. If you look at this, what they're saying is, if you look at R1 distillation, for example, and we'll talk about easy, medium, hard token prediction, but let's just stick to any one of them. Let's take hard. From 1.41% prediction, reasoning token prediction accuracy, it has gone to 23%, which is a huge lift. Right? So especially for hard problems, hard tokens to predict. So this is the core result of this paper. And they relate it to a neural scaling law. That is another interesting. They posit a neural scaling law for which actually they don't give any evidence of what it is. But I suppose at this moment it's a hypothesis. But that is the sketch of this paper. With that sketch of the paper, I suppose, I would like to go now. If there are any questions on the broad, what is the core result of the paper, I'd like to take that.
Okay, so it's very interesting. This one is a little bit more challenging for me, so I appreciate everybody's patience. So it sounds like what's happening is they're taking Qwen, you have this model, you have Qwen, then what they do is they before doing any other step, it sounds like they're applying GPRO for it first. And then they start training, and that is what the breakthrough of this paper is, because then you can achieve a lot more accurate results, and it's amazing. Is that correct? Do I got it?
Close. I'll phrase it this way. So first is when you say Qwen, it isn't Qwen. It is Qwen with R1 distillate in it.
Okay.
R1's reasoning distillate into it. R1 itself, if you remember, used GRPO, right? So they take the Qwen, which is the traditional model, with R1 distillation into it through supervised fine-tuning. They call it the base. And then what they say is, if this is a base, imagine if it were a pristine model, untrained model, what would you do? The first thing you would do is a next token prediction task you would give it. But they're saying we will take that model, Qwen with R1 distillate in it, and pretend as though we need to do next token prediction training again. But this time when we do it, we will do it with GRPO, reinforcement learning, and specifically with GRPO all over again. But the task is different. The task now is next token prediction. And then you're right, at the end of it, the model that emerges, they find that not only is it much better, but you let the rest of the whatever people do with the model, namely the supervised fine tuning and further RLHF, etc., they observe that the lift or the superiority of this approach continues to stay throughout the process, and you end up with an overall model that is generally superior.
Very
Elsa, did it
interesting.
make
Yes, thank you.
So that is what this paper is about. It's remarkable, actually. They just go back and apply RL to the next token prediction itself, which is the classic pre-training step. Yeah? And that's why the title of the paper is Reinforcement Pre-Training. Right? So with that, any further questions, guys, before we walk through the paper carefully? I'd like to also make a comment here. There's a debate, there's a sort of a discussion in the research community that does RL with verifiable rewards, like we are doing with using GRPO and so forth, does it actually induce new knowledge in the LLM, or does it just accentuate or sharpen existing knowledge by redistributing the probability weights? It's sort of a technical point. And many people are coming to the belief, there's emerging research from Anthropic and DeepMind that perhaps it's just accentuating, predominantly it's accentuating the prior learning. I personally believe that RL is more than that. It does. For example, how do you otherwise explain the spontaneous emergence of reasoning in R1? Now, leaving that aside, the way this paper sort of falls into the debate is, when you look at this fact and you say you go back to tokens, after you have done, prior training, like when your base is a Quen with R1 distillate already in it, you use that as a base. It means that it has gone through a next token prediction process. It has gone through supervised fine-tuning process. Then you go back to reinforcement learning for the next token prediction. Is the lift or the improvement in accuracy because it is accentuating or sharpening prior learning? This might be a contributory evidence to such a hypothesis. Right? And it is a thought that I was left with. This paper does not actually explicitly address that discussion, but this was the thought that I was left with at the end of working through this paper. Nevertheless, it's a very interesting contribution, and thank you for the community for suggesting that we do a paper reading on this. I will now carefully read this paper. The abstract says, in this work, we introduce reinforcement pre-training as a new scaling paradigm for large-scale language models and reinforcement learning. Specifically, we reframe next token prediction as a reasoning task trained using RL, where it receives verifiable rewards for correctly predicting the next token for a given context. RPT offers a scalable method for leveraging vast amounts of text data for general purpose RL. This statement is I suppose, the practical utility of it. Not only does it lead to superior models, think about it this way. Applying RL at scale has always been hard because it's hard to get such data, expensive to create such data. However, by converting next token prediction itself into an RL task, suddenly it opens the door to using those trillions of tokens that companies have scraped. And they all now become fodder or the data for the reinforcement learning training. Right? That's an important thing to mention, rather than relying on domain-specific annotated answers here. So this is a very important point. By incentivizing the capability of next token reasoning, RPT significantly improves the language modeling accuracy of predicting the next tokens. Moreover, RPT provides a strong pre-training foundation for further RL refinement tuning. So what it says is, after RPT, after this process, treat it as any other pre-trained model. go do your stuff. You do whatever you were doing after that, further supervised fine tuning, further RLHF, whatever you are doing, do that. And when you do that, you will observe that it consistently improves. Right? The improvements remain. If anything, they get even better. The results posit RPT as an effective and promising scaling paradigm to advanced language model pre-training. That's what they're saying. Right? So I will leave the cherry on top cake argument and go to the main contributions of this paper. Right? And just there's also, for those of you who are technically inclined, maths inclined, one aspect is, see, when you do just next token prediction with a negative log likelihood loss or something like that, what happens is it's sort of a greedy thing. You just have to get the next prediction token right. When you do RL forces a wider, especially GRPO, it forces a much wider exploration of the vocabulary to figure out what could be the right answer. And I think that is probably the reason the improvements are coming in this paper. But so anyway, that's my speculation. I'd like to hear what you folks think. Our contributions are summarized as follows. We introduce RPT, a new scaling paradigm that reframes next token prediction as a reasoning task trained with reinforcement learning, utilizing intrinsic verifiable rewards derived directly from the pre-training corpus. That is a key contribution. Then it says RPT offers a scalable and general purpose approach for the simple reason that you have way more data. RPT significantly improves next token prediction accuracy. So what it says that not only we show a new method, we should also show that this method works. It leads to significantly better prediction accuracy. And then the fourth point they make is RPT yields a stronger pre-trained foundation for subsequent. And then, of course, you use this model for subsequent work. Then, sure enough, it's a better model to start with than the traditionally pre-trained model. That's the main statement of this paper. And so we can see a reasoning trace. See, if you have a standard next token prediction, electric force grows with charge, size. Prediction should be size. Right? And here was the actual corpus. Electric force grows with charge size and decreases with distance squared. This is Coulomb's law. It explains how charge objects, etc., etc. Now observe. So obviously you notice that the machine is doing a lot of compute and thinking. And this is actually what it produces. It produces a lot of tokens, actually. To produce one token, it produces quite a vast amount of tokens. And then it says that comes under the think bracket. And then it concludes that the right word is think. So it says, to determine the next token, let's think about what would logically come next in a text, since we mentioned blah, blah, blah. And it goes on reasoning. Those of you who are familiar with and have played with DeepSeek R1 know how hyper analytical that R1 gets when you ask it to think, right? When you give it a question and it shows you the thinking trace. So that is that. Now, the rest of the paper is actually fairly straightforward. If you get that idea, this is all it is. It's formulating it as in a bit of math. Next token prediction is, of course, predict the next token, xt, given the fact that you have the prior token and a model theta, right? A state of the model theta. This is your objective function, right? On the other hand, reinforcement learning, which it thinks in terms of rewards, it just says that suppose you know the question and you know the answer, right? In this particular case, what is the next token? What you do is you have the LLM in a certain state, parameter state, repeatedly give it the same question, and then you get G answers, right? So you get many answers, outputs. The pi theta, roughly speaking, is RL speak. Basically, it means it is the current state of the model parameters. It's called the policy network. a deterministic verifier calculates a reward function. What is the deterministic thing? Very, very simple. We covered it in the next image. Literally 1 for the right answer, 0 for all other possible answers. And that's all it is. That's all that this paper says. And then it says that, so how do you, like, in reinforcement learning, you say that the reward is accumulated over the steps of a trajectory. Like you are in state S1, you take a step 1, you take a step 2, you take a step 3, and then you take a terminal step, ST. For each step in reinforcement learning, you give a reward, R1, R2, R3, RG. Now, in this particular problem, what are those steps? These are literally the tokens being produced by the machine. Right? It produces a certain token, and for that token, you have a reward. And the trajectory or episode is essentially the entire output that the machine has produced, right? And you talk about, obviously, the reward for the entire trajectory in these things. So they do mention that they limit the size of the trajectory. During training, we adopt a 8K, sorry, I should erase this and use the right color. During training, we adopt a 8K training length. So then they give you some details and a batch size of so many questions. They take the group G value in the GRPO is 8. In other words, they repeatedly ask the LLM to produce the answer to the same question 8 times. And so the group is made up of 8 answers. And that is it. That is what this paper is saying. The rest are experimental results which speak for themselves. Then comes an interesting hypothesis they make, which actually I did not find anywhere the data for it. So let me interpret this. If you're familiar with the neural scaling laws, which I'll give a very quick intro to, the neural scaling laws, which were discovered in 2020 with OpenAI, and that were very influential in the evolution of LLM. It says the following: as you scale up the compute, as you scale up the data, right, and scale up the model parameter, then your next token prediction accuracy will keep climbing up. In other words, the loss function will keep going down, right? And there is a theoretical optimal limit, right? What would be the least loss function that you can possibly have in such a scenario if you had infinite compute and infinite tokens, right? And there is an equation that the neural scaling laws give, but the basic intuition is, hey, you want a smarter model, just get more data, make the model bigger, and train it for longer. That is it. So in the same way, in the same spirit, they posit a scaling behavior. And so they say they model, here they use the word model, and it is not very clear that they're positing a hypothesis. To me, it seemed that they're positing a hypothesis because I went through the whole paper. Nowhere could I find the values for A and P star and alpha, but I'll interpret it for you, what they are really trying to say. They're trying to say is that, let's say that the prediction accuracy, actually this statement, I would write it slightly differently. I would have written it as maybe, and color me. So I would have written it slightly differently. I would have written is that the prediction accuracy is the absolute theoretical prediction maximum that you can achieve ever, minus this quantity, what I would call minus A over C alpha. Right? So C is your compute, that how much compute you brought. Alpha we don't know, A we don't know, right? So I would have said minus B. Let me put it as B, where B is equal to minus A, right? And B is a positive quantity. What is not very clear in this, that if you really think through this equation, you'll realize that A has to be negative because the accuracy has to be less than a theoretical maximum accuracy that you can achieve. Right? So what they're saying is that you have, like if you really look at the next token prediction accuracy, that it will go up to, let me use black, that it will go basically up to asymptotic limit. They posit that it will rise up to an asymptotic limit because accuracy cannot keep going up and up and up, right? And that asymptotic limit is your P star. And so at any given moment, you bring less than that quantity of compute, then the accuracy, so the accuracy that you get will be less than the theoretical maximum, right? I don't know if I lost you, but I'll restate it. What they're saying is that imagine that if you just went on computing, kept on doing reinforcement learning with the tokens that you have, then what would happen is you would achieve a theoretical maximum prediction accuracy, which is P star. In reality, however, because you don't go on computing and you bring only so much token and so much compute, therefore the prediction accuracy is less than that, and it scales up. The like the blue line is sort of a scaling law. It says you keep on bringing compute, RL compute, this C, and as you bring in the compute, it keeps scaling up, right? And till it achieves P star as an asymptotic limit, right? So PC at the see, think about it this way: when C at the bottom denominator is infinity, the first term will disappear, and what will remain is the theoretical maximum, right? So it asymptotes there. That's what this scaling law is trying to say, and that is it. That is it. They give you some related works and examples. So to recap, what this paper says is that why not bring RL and to the reinforcement learning, and in particular GRPO, directly to the next token prediction task, which is a classic pre-training, LLM pre-training task. And let's see what happens. But when it does that, it's worth noting that it doesn't start with a model that is completely pristine, that is just randomized weights. It starts with a model that has already gone through the standard next token prediction pre-training. And it has further gone through some further distillation, supervised fine-tuning through R1 distillation. So they happen to take that as a base. And I suppose in future research, people are going to revisit it and say, what happens if we do this? What happens if we do that? What happens, for example, if we just don't bring in the R1 distillation, or we don't bring it in such a pronounced way, or so on and so forth. I'm sure there'll be a lot of downstream work, I assume, and that is so this is how I understood the paper. It's a very interesting paper. With, that's it. That's all I have.
Yeah, Asif, one question. While they show the improvement of the 14 billion parameter and it tries to reach the 32 billion parameter model, what is not clear is the cost, because obviously doing reinforcement learning for next token prediction has its own cost. And what we saw in that example, just to predict the word size, it had to go through the entire process of thinking. So that part is still not clear for me.
Absolutely right. See, Pradeep, that's a very astute observation. See, it is true. Pre-training is the most expensive part of the training process, next token prediction, pre-training. And we are saying, hey, let's go revisit it. You say, are you kidding? That's expensive, you would say. But here is what makes it, at least for this paper, it makes it reasonable. First of all, they did not actually use the web scale data. They used the OmniMath dataset, which is a relatively small dataset. But they did the RL for next token prediction on a fairly limited dataset for about 4,000, I believe, 4,000 odd data points only. Yeah. And already they got a remarkable lift. So I suppose they left it as an open question of what would happen if you applied that to web scale, because I did not see that done here. The second thing that is there is that, see, if you take a smaller model, then, and you can just do some more RL reinforcement pre-training on it, and you can get the same sort of a prediction accuracy as a much larger model. It is really worth doing, because smaller models don't cost as much to pre-train, even if you're doing RL pre-training. Right? So those are two mitigating factors here.
Got it. Got it.
So there's a lot of, what's the phrase? There's a thundering silence here at this moment. I don't know if I explained the paper clearly. Give me some idea. Any thoughts, any questions, guys?
No, at least
I have a thought. Go
explain.
ahead.
Sorry, you
No, it's fine.
explained it clearly. We understood that also, but I think it will take some amount of rereading and trying to grasp the concepts and come back on it.
That is certainly true, Pradeep. See, this paper presupposes that you're intimately familiar with, obviously, the whole Instruct GPT process, and you're also intimately familiar with reinforcement learning. In particular, intimately familiar with the DeepSeek R1 research paper and the GRPU. Because without that context, this paper would be very hard to understand.
Yeah, and thanks to the 2 classes I've taken with you, I'm familiar with both of them. So yes.
Nice.
Yeah, I agree. It's an interesting insight. It's just, and I'm lightly familiar with those concepts, and even then, I think also it's their writing style personally. I think that impacts how the information is relayed. But something that you mentioned that I thought was really intriguing, if you scroll down to the graph where you were mentioning how it's asymptotic,
Yes.
this is where you're like, hey, what are some people's thoughts? So something that comes to mind for me is it makes me wonder as like you approach like as you have more and more compute and you're getting further to the line of it being asymptotic. And maybe Sam Altman would argue that eventually you could reach AGI. So it makes me wonder if that's true or not, but if make all, would that reach above a human brain in terms of getting, 100, at least 100% accuracy. So anyway, that's just a thought I had when you mentioned that, and I thought I'd share it with you.
Yeah. I see. Thank you for sharing that thought. What I find is the concept of AGI is so nebulous. And now we have a completely different term. We say artificial superintelligence, which is to be distinguished from AGI. And if you ask 2 people, how do you distinguish AGI from ASI? Both of those people will give different answers. And so the whole concept at this moment is nebulous. There used to be the Turing test, but most researchers believe that these models have already become so smart that Turing test is long past. Right?
Yeah, I
So,
agree.
yeah, and when I look, for example, at this one, the Grok 4, I look at O3, and I look at Kimi that just came out, the new Kimi that just came out, which is amazing, absolutely amazing. All of these models. When I look at it, my own interpretation, I would agree with Sir Geoffrey Hinton when he says that these models are already thinking and they have achieved artificial superintelligence.
Yeah.
Always surprised. Yeah.
Yeah, I agree with that too. I've been thinking about that for a while. It's like I feel like we've already approached that because of just how like if you would have asked someone before it came out, like, hey, what do you think if a computer could do this? They would have a very different insight. But then now when you ask people what their insight is because they know what the LLMs can do, then the bar keeps moving. So I certainly agree with that.
There is one point in the paper that I forgot to mention. How do they determine whether the next token that you are predicting, is it an easy, medium, or hard? Right? Because they have separate results for how well it does for easy tokens, how well it does for medium tokens, and how well it does for hard tokens. Actually, that's fairly straightforward. What they do is they take the base model. Whenever you give an LLM, and I thought this point I just mentioned in case one thinks about it. You take an LLM, and what it actually produces is a probability over the vocabulary. So again, I'll go back to my Aardvark and my Zephyr, right? And by now, you folks must be, if you have been with me here for a while, the happy cow, you must be perhaps getting tired of the happy cow. There. And then here's the word moon. And even though you said that the moon has a pretty significant bump in probability, let's say, you still do a sampling of the softmax. These are your softmax probabilities that it produces. What happens is LLMs have this quality that perhaps people don't quite remember as often, that LLMs don't just produce the next token. They actually don't. First they produce this probability distribution, and then you sample off the probability distribution to pick the next token. Right? It's a nucleus sampling or some sampling, and then you pick the next token. To the extent that you have this probability distribution, it has some crucial information. It tells you how confident the LLM is about the next token. How easy or hard is it finding to predict the next token? And that is measured as entropy. So if you just do pi log pi, which is your measure of entropy edge, this will give you a sense of the sense of how hard the model thought it was to predict the next token. Right? That's a way. And they sort of mention it somewhere, I believe, yes, in the experiment. In fact, we are staring at that line. We categorize token positions in the validation set according to their difficulty. Specifically, we calculate the entropy at each token position using the base model. So what they do is they use the base. This LLM is the base that we talked about, which was your R1 Destil Quen 14B. I'll just call it base. And then you determine that your new RPT trained model, base model thought it was difficult. How well did your RPT do? And this base model thought it easy. How well did the RPT do? That's how they have categorized the easy, medium, and hard, right? So then they go on to say, we then designate positions as belonging to easy, medium, or hard. The splits if their entropy exceeds the threshold of 0.5, 1, and 1.5 respectively. So the idea is that the higher the entropy, the more underconfident an LLM is. And by the way, this also relates to an interesting fact, which is that people have observed that models, they begin to hallucinate. If you start looking at where do they start hallucinating, there was some evidence that right before it starts hallucinating, it begins to lose confidence. Like you can see that the entropy of the probability distribution is pretty significant, pretty high, right when it is beginning to hallucinate. Right? In fact, that is what many people, for example, when they do RAG implementations, they watch out for that. And if they notice that entropy has already crossed a certain threshold they have in mind, they abort it. And then they revisit it with more data, more something. They say, how do we fix this situation? Maybe we need to search into the retriever system a bit more. Okay? So there is that for what it is worth. And the other question that I don't think was mentioned and is certainly worthy of asking. Okay, so now that you have done RPT, how, at least I didn't find it mentioned. The first question that comes to my mind is, and you have specifically like, does it at all affect the hallucination factor of the LLM? So if instead of starting with a base typical pre-trained model, if I start with the RPT model and then do my rest of my post-training, do I see diminished hallucination in the model or not? I don't think that question was addressed anywhere in the paper. But I may be wrong. If anybody else has been studying this paper, please let me know.
Can you repeat that question? Oh, sorry.
You see, models hallucinate, right? And there's a certain hallucination rate. The question is, if I start with RPT as a base, and then train a model for whatever downstream task I'm training it for post-training, at the end of it, I have a model that I'm using for some practical purpose. Do I see any improvement in the hallucination problem of LLMs? Hallucination is defined as the model just making things up. It does it occasionally, but it does it less and less these days. Nevertheless, it has stayed as a persistent problem. So one of the goals in our community of this has been, how do we make the model hallucinate less? And the question worth asking with this paper is, does RPT in any way affect the hallucination rate? Does it make any improvements to the chance of hallucinating in a model? So to my knowledge, this paper hasn't addressed it.
Well, one thing that they say, like they show the accuracy. So I would think you would be able to kind of line up those same numbers to what is available for larger models and see how often they hallucinate. And that might be a way to kind of eyeball it, perhaps.
That is true. See, if you believe this thing, this hypothesis that entropy shoots up right before hallucination, one of the nice things is, because this machine is reasoning, I would have imagined that there should be a significant section somewhere in the paper, which I probably missed, but which would specifically show that reasoning causes it to not make things up, that it causes it to therefore hallucinate less. But I was searching for it all over the paper. I don't remember finding it.
But the data set that they have used probably is not sufficient to actually arrive at that conclusion, right? Because it's just the
Very
omni.
true. Very true. I mean, see, this is a sort of feasibility study paper or
Correct,
a
correct,
proof of
correct.
concept. It started with OmniMath, which is actually a very small data set.
Yeah.
So a lot of work is needed. I would say that. And I think one of the mentioned, Elsa, you mentioned that the language is not very clear. I hope you're referring, I don't know whether you're referring to my language or the language used in the paper.
Oh no, no, I'm talking about the style of the paper, like the way they present their writing style. That's what I'm referring
That's right.
to.
That actually, even I agree, because look at this, and I just bring this equation here. It's a pretty odd use of a word. All they want to say is that if you pick in equation number 3, if you just pick the right token, you get a reward of 1, otherwise 0. They could have said it in so many ways, but they, in order to say it in the most precise way, they use also, ultimately a token is a member of a vocabulary, word, subword, punctuation, whatever it is. But they say it in a very formal manner. They use the concept of LG, the length boundary. And then of all the symbols that they could have picked, of all the symbols in the world they could have picked, they picked the symbol that people usually reserve for the loss function.
Yeah.
Do you notice that? And for the longest time, I kept on looking at this and saying, why did they choose? Are they trying to clue something or hint at something? Why does it look like the loss function? Right? And then you realize that it's just an idiosyncratic choice of symbol. Right? And what is wrong by just laying it out by saying RTI is equal to 1 if you got the ground, if the token matches the ground truth, 0 otherwise. Right? So I suppose it does. I mean, I would agree with you that the language could be a little bit more clean or explicit about it.
Yeah. I will say just kind of because we're on the topic of that, like, um, maybe like earlier this year, I have a friend, who, uh, has a very strong background in math, like really strong, we'll just put it that way. And he sent me this math problem and he said, I want to see if my students are cheating. And so I've been working with him. He's like, is my prompt wrong? Like, what's going on? And I've been working with him to see if the newer models. So I plugged the latest one. I haven't plugged it in 04 yet. That's on my to-do list. But on 03, it would get the answer right, which was better than the previous models. But it still hallucinates quite a lot. So that's what I thought I would share because um, if it's gonna hallucinate there, it's gonna hallucinate here. You know what I mean?
Yeah, though I would say that, see, none of us know how O1 or O3 was trained because OpenAI has not revealed any details. But
Mm-hmm.
but there was an observation which may not be true anymore. When O1 came out, people observed to their surprise that it was hallucinating more than the 4.0.
Hmm.
That was widely recognized that that was happening. And then I don't know whether by O3 they have fixed that or not. Probably they have, or at least they have tamed it down quite a bit. But what you are saying is that you notice O3 hallucinates more than 4.0.
So
Is that
what we that 4.0 they all actually okay. So in in 4.0 it never got the answer right, and this is a graduate level math question. So it never got
okay?
the answer right. And then I kept trying every which way, but and sometimes he and I would get the right answer, but it was random. Then in 03, it gets it right, but then he'll throw other questions at it to back up the answer, like use X, these things to do it, to look at it, right? And then it hallucinates that. So it's getting
Right.
better, but it still hallucinates. So we both find it pretty
Yeah.
interesting.
Yeah, no, that's very interesting. Murli, I'm reading your comment. There's an argument published that credit distribution in RL with GRP boils down to SFT. See, I've seen that argument, and thank you for reminding me. It's a very good thing, and I don't know if people know. There's a wide discussion happening. I'll just mention Murli's point. A wide discussion happening, and there's research from DeepMind, Google DeepMind, from Anthropic, etc. That begins to, again, the position that I mentioned, that RL with verifiable rewards, RLBR as it is now called, specifically GRPO, with GRPO, it is just accentuating or sharpening the signal by redistributing the probability masses. And I've been closely tracking it. I have a few, broadly, I do agree that predominantly, perhaps it happens, but I am still somewhat skeptical of agreeing with that strongly for two clear reasons. First of all, composability, then it may compose ideas. Reinforcement learning, what it does is, or to my mind, one of the key benefits of reinforcement learning is it has an exploration versus exploitation trade-off. In particular, because you have to explore larger in the vocabulary, you're much more likely to stumble upon the right word and then get reward for it, at least, especially with GRPU, because you're taking a whole group of answers. So there's more exploration going on. Whereas the supervised fine-tuning, the negative log likelihood of the next token prediction, is a very straightforward. It says, okay, the probability of the correct token you produce is low, just bring it up. Right? So it's more of a very point local answer. And so, to my mind, yes, GRPO does lead. I don't know whether I would agree with the statement that it doesn't learn new things. I do believe that it can learn new things by generalizing from the existing internal concepts that it has built. Right? And so anyway, we'll see where it all leads, but I would not dismiss RLVR so easily. In practical terms, it works. At the end of it, a big milestone in machine learning, in AI, will forever be remembered that DeepSeek R1 was the first open source model that showed that don't try to induce reasoning in machines by supervised fine tuning with chain of thought examples. That will not make the machine think. Instead, do nothing, step away, just apply pure RL and keep on giving machine time to learn. Give it a lot of computes, and sooner or later you'll see, and there's a beautiful result in that paper that is frankly breathtaking, that spontaneously the machine begins to reason. I have never seen the rise of spontaneous reasoning in any supervised fine-tuning model, at least nothing in the published literature. I don't know if that adds anything, Murali, to your thoughts. But thank you for sharing that valuable insight. Would you have anything to say there? Yeah, if you could please speak. Anyone
found-
else? All right, guys, if there are no other questions, I suppose we'll end for today.
Yeah,
go
I
ahead.
just had one thought rather. So if you say that RL just sharpen the knowledge, it's kind of you take the knowledge, you sit with it, and just like what we hear, like sand, like in a water, settle it down, like in a water. It is that kind of a process. Is it right word to say, like a right analogy to say?
Yeah, sort of. That is what some of the emerging research is showing. That it certainly, in many cases, I'd say here's how I would say. In many cases, it redistributes the probability mass. Remember the probability distribution over the vocabulary that we said. It redistributes the probability mass in such a way that the signal gets stronger, right? It's more likely to be the right answer. However, I would not discount out RLVR as being just that. To me, it seems about as useful an argument as saying, I eat bananas, therefore I eat nothing but bananas. Right? It may be capable of synthesizing new knowledge simply out of the existing knowledge it has, simply because composability is still there, exploration is still there as key virtues with the RL.
Yeah. So I had like a next question based on that. If let's assume in terms of reasoning, so there is this knowledge, like out of distribution knowledge. Like you see some kind of a data and you try to build the reasoning on it. So do you think with this approach, with this RL approach, are we able to capture the unknown domain knowledge? To give you example, before COVID, like COVID never happened. So to predict or to guess what will be happen after 5 years was very difficult guess. Like if I ask you, what would be happen with the laws and policy if alien come down in our generation? What would be work life situation look like? What would be policies? What would be temperature in a work life space? So my question is toward like how RL will approach toward out of distribution data or unknown data.
Generally not. See, these are black swan events. And literally, it's like, for example, COVID hit. Nobody could have predicted that a COVID would hit. Right? Whether it was a lab escape or whether it was human engineered mischief or whether it was naturally caused from bats, who knows? The fact of the matter is it was a black swan event, extremely rare event that nothing can predict. And likewise, the trajectory that COVID took is a superposition of so many causal factors. Human psychology. Some people use masks, others people didn't. Some people stayed at home, others didn't. Theoretically, if you ask from a scientist, for example, the epidemiology with the SIR models and so forth, they would say that if all of humanity just stayed home for 2 weeks, COVID would have disappeared in 2 weeks. The trouble is human beings are not willing to do that, right? Because some people think it's a hoax, some people think they don't take it seriously. Some people say that I take it seriously, but I still need to go earn my livelihood. I can't do without it. Right? And some people you simply can't do without. All of the cops in the city cannot say that we are not going to keep the city safe for 2 weeks. We are all going on leave.
Mhm.
So all the other factors kicked in, and so COVID ran its trajectory. And I think those trajectories are it can be simulated to some extent, but I think it's not something you can immediately get straight as an answer from a model at this moment.
Mm. Yeah. And my intent of asking question was from like a creative um, perspective that what I thought may be wrong, that creative thought or creativity mostly originated from unknown distribution.
Oh, that is
So
already, there is creativity in the machines. You probably know alpha geometry was the first one that managed to create new results in mathematics that were truly, genuinely new results, right? Discover new results. And not
Mhm.
new results in some very arcane way. For example, think of a simple shipping container.
Mhm.
Any businessman would like to ship goods in the shipping container, not empty air, right? So they would like to pack the container as much as possible. They charge by the container. But since boxes come of different sizes, how do you optimally pack the container has been a problem that mathematicians have worked on for decades. And whatever was the best algorithm, alpha geometry, I believe, outdid it. Right? And likewise, it solves one of the favorite problems of the great mathematician Terence Tao, that he called one of the sort of almost like a North Pole problem, North Star problem. And alpha geometry made a dent into that problem, created a solution that no humans had discovered. And it is happening now. These machines, don't underestimate them. They are soon going to be the ones who will make the next round of discoveries. We are probably the last generation in which scientific discoveries are made by humans. Majority of scientific discoveries are made by humans. I think going forward, majority of scientific discoveries will be made by machines. It's already happening. Look at Alpha Evolve, the research work. Maybe we should cover it. I'm surprised
Yeah.
nobody's suggested that I should cover that in weekly paper reading.
I guess AlphaFold is also like on same line, is like great paper
Absolutely.
on that.
AlphaFold is
Yeah.
ancient history. Nevertheless, it had profound implications on medicine, and
Yeah.
very deservingly it got the Nobel Prize last year.
Mm. Yeah.
All right, guys.